In a monumental breakthrough that is transforming how humanity perceives the cosmos, the James Webb Space Telescope, JWST, has achieved what was once considered purely speculative science fiction: the discovery of what appears to be an entirely separate universe. This astonishing revelation emerged during a deep field observation campaign aimed at studying the earliest stages of galaxy formation. Rather than merely identifying new galaxies or clusters, Webb's instruments detected an unusual region of space emitting signals so strange and completely unexplainable by known physics that the scientific community was forced to entertain a possibility long confined to theoretical speculation: another universe. Before we begin, don't forget to hit the like and subscribe buttons for more updates. The discovery happened when the telescope, while capturing infrared light from the farthest reaches of spacetime, recorded a signal pattern that defied all current models. These signals did not match any known cosmic microwave background signatures, nor did they align with expectations for gravitational lensing, quasars, or any high-energy phenomena within our own universe. Initially, the data seemed corrupted or misinterpreted, but repeated observations confirmed the anomaly: a region at the farthest observable distance beyond the epoch of reionization, emitting structured yet unclassifiable signals. This area, first dismissed as a statistical outlier, consistently exhibited energy distributions and structural patterns unlike any galactic formations known in our universe. The laws of physics, as we currently understand them, appeared subtly distorted in this portion of space. Gravitational behavior, light refraction, and thermodynamic interactions within this region were all anomalous. The readings suggested not merely a cluster of stars or galaxies behaving unusually, but an entire system governed by a fundamentally different framework. As more time and observational resources were devoted to this phenomenon, it became increasingly apparent that the James Webb Space Telescope was not only looking far back in time, but potentially sideways across the very fabric of existence. The data suggested a separate continuum of reality, not merely an extension of our known universe, but a distinct, closed system. The implications were profound. If the signals truly originated from a separate universe, then the JWST had expanded the boundaries of cosmological science beyond the Big Bang and into the realm of the multiverse. The concept of a multiverse, a collection of parallel or alternate universes, has long been a speculative offshoot of quantum mechanics and string theory, yet it has never had empirical evidence to support it. Until now, the Webb telescope's infrared capabilities, far exceeding those of Hubble, enabled it to peer into a realm where such phenomena could be not only detected but also measured. This potential signature of a multiverse consisted of what researchers began to term quantum interference cosmology: light waves exhibiting interference patterns that defied the conventional physics of our own spacetime. In practice, this meant Webb might have glimpsed the edge of our universe, where it touches or perhaps grazes another entirely separate domain. The energy patterns resembled neither dark matter interactions nor gravitational lensing distortions. Instead, they exhibited a coherent and repeating arrangement, like a cosmic fingerprint from beyond known space. The more the team analyzed these patterns, the clearer it became that they were not echoes of our own universe reflected through warped spacetime, but the structured layout of formations governed by entirely different laws. Astronomers and physicists began to question fundamental cosmological assumptions. Our universe, long considered the entirety of existence, might be just one among many, each with distinct values for fundamental constants, unique timelines, different physics, and perhaps even alternative forms of life. What Webb detected could be more than just another galaxy cluster or supervoid. It might be the visible boundary of another universe that, through some unknown mechanism, has become observable from our vantage point. This potential bridge or window between universes might be explained by cosmic-scale quantum entanglement or even brain collision models derived from higher dimensional theories. Some speculated that this was a fleeting cosmic alignment, a momentary convergence allowing light from another universe to bleed into ours, creating a sort of aperture in the fabric of reality. Others proposed that this region might be a permanent interface where multiple universes coexist in delicate balance without ever fully merging. Theories once limited to thought experiments were now being reconsidered in light of actual data. The significance of this discovery extends beyond academic curiosity. If confirmed, it could offer an unprecedented chance to study the conditions of another universe and compare them to our own. Understanding these fundamental differences might unlock answers to some of the most profound questions in physics. Why does our universe have its specific physical constants? Why is there something rather than nothing? What triggered the Big Bang? Answers that have long eluded scientists may now become attainable by examining this neighboring realm. This newfound universe revealed more than just alternative galaxies. It suggested a framework where even the concept of time itself appeared nonlinear. The light patterns indicated that the flow of time in that universe did not correspond with our own. Some areas within the anomaly appeared to oscillate rhythmically in brightness, as if time itself pulsed on a different rhythm. The implications for theoretical physics were profound. If time and space could behave differently elsewhere, it suggested that our own understanding of reality is more local than universal. The very foundations of physics, relativity, thermodynamics, and quantum mechanics might be just one of many possible frameworks. Excitement within the scientific community was palpable. Observatories worldwide began coordinating follow-up observations across different wavelengths to verify Webb's findings from multiple perspectives. Radio telescopes, X-ray observatories, and neutrino detectors joined the effort. Although none could match Webb's depth in the infrared spectrum, corroborating evidence started to surface. Slight deviations in the cosmic microwave background near the anomaly, unexplained energetic particles arriving in Earth's upper atmosphere, and unusual gravitational wave patterns hinting at disturbances beyond our cosmological domain all reinforced the mystery. This revelation sparked a surge of theoretical exploration. Astrophysicists began modeling how such a universe could exist alongside ours without violating conservation laws. Some proposed multi-dimensional membranes, envisioning universes as soap bubbles within a higher dimensional foam. Others revisited the idea of bubble universes forming within a cosmic inflation field, where random quantum fluctuations could give birth to entire realms. These were no longer mere speculative sketches on chalkboards. They became potential blueprints for explaining observable reality. With every new observation, Webb continued to deliver clearer, more detailed images of the anomaly. It soon became evident that this new universe had its own form of galactic clustering, though arranged in a fundamentally different pattern. The structures observed were neither spiral nor elliptical but appeared interconnected in fractal-like geometries, possibly influenced by alternative gravitational forces. The light from these formations was shifted not only by distance but also by an unknown process that altered its spectral signature. Whether due to time dilation, space curvature, or an entirely foreign physical effect remained uncertain. As these images spread worldwide, they captured the public's imagination. The media struggled to convey the discovery's significance accurately. For many, this moment rivaled Galileo's first telescope but was amplified by the profound realization that not only are we not at the center of the cosmos, we might not even exist within the only cosmos. Religious, philosophical, and existential debates naturally arose, but the scientific community remained focused on understanding, measuring, and ultimately explaining this phenomenon. Every day, new insights emerge from the wealth of data streaming in from Webb's instruments. As artificial intelligence systems analyze the vast streams of data, they continue to uncover inconsistencies with known universal behaviors, further reinforcing the idea that this is not simply an unusual region within our own universe but rather an interface with another. The focus of inquiry has shifted from questioning if this is real to exploring how it is possible and what it means for humanity. What makes this discovery even more thrilling is that we are only at the beginning. Webb, still in its early operational phase, continues to refine its focus and increase exposure to the anomaly. With each image and measurement, we are laying the first observational groundwork for what could become the science of interuniversal cosmology. Instruments designed specifically to target such anomalies are already in the planning stages, inspired by this singular moment of insight provided by Webb. If you enjoyed this video, please like it and subscribe to our channel. Also, leave your comments below and share your thoughts on the James Webb Telescope potentially finding another universe. What could this mean? We want to hear from you. Thank you for watching, and see you next time.